Well, welcome to our video for statistical concepts and market returns. We're going to start out with some definitions. When we talk about descriptive statistics, it's just that they describe a large data set. So a descriptive statistic might be the mean or average of all the values. So that would be a descriptive statistic, describing where the distribution is centered. Inferential statistics uses a sample from a population to make a probabilistic statement about the characteristics of a population. So, we've got a big barrel of balls, ping pong balls, and they all have numbers written on them. Returns, if you like. And we don't know what the mean is. Well, if we take 10 balls out of there and add them all up and divide by 10, we've got what we call a sample mean. And based on some assumptions about the distribution of those numbers on the balls in the barrel, we could make a statement about the mean and say maybe, well, we're 90% sure the mean of all the balls in the barrel is this interval. So we're making an inference about the true mean from the sample mean. So that's inferential statistics. And we'll certainly get enough examples of that. A population just is a set of all the possible outcomes. And that sometimes depends on how you phrase the problem. But in general, population is we have all the possible outcomes. So if we take the mean, we've got the true mean. And a sample is a subset of all the possible outcomes of a population. Now we've got 4 measurement scales. We're supposed to be able to distinguish among them. And we've got NOIR there, noir, the French word for black, just as a way to help you remember nominal, ordinal, interval, and ratio. In a nominal scale, only the names make sense. So it doesn't tell us anything about the order, the intervals, or the ratio. And as an example, think of you had a bunch of birds, you had to separate them, categorize them as either a robin, a parrot, or a hawk. Well, I think most of us could do that, but that's the only thing we can say about it. Now with an ordinal scale, the order makes sense. So if we have labeled some stocks, large capitalization, small capitalization, middle capitalization, based on the total market value of their outstanding shares, the order would make sense. A mid-cap stock has a greater market value than a small-cap stock, and a large-cap stock a greater market value in total than a mid-cap stock. But the intervals, the difference between large cap and mid cap and the difference between mid cap and small cap, that's just not defined here at all. For an example of an interval scale where the intervals make sense, we use degrees Fahrenheit. And we know 40 degrees Fahrenheit is 10 degrees greater than 30 degrees Fahrenheit. And 50 is 10 degrees greater than 40. So the intervals make sense. What doesn't make sense is the ratio. Is 40 degrees 4 times warmer than 10 degrees? Well, I don't know, probably not. Certainly if you've lived in a very cold climate and you went out one morning, it was 1 degree, and the next day you went out and it was 2 degrees, I don't think you'd be saying, gee, it seems twice as warm. The ratios just don't make sense. And the reason they don't make sense is because 0 degrees Fahrenheit is not absolute 0. So for the ratio scale, let's take an example of something where 0 is 0, and that would be money or wealth. If you've got 0, you've got none. If you've got $200, you have twice as much as if you had $100. So when there's an absolute 0 on the scale, the ratios make sense as well. So you'll be called upon to identify which type of scale some various measurements are. So some more terms. A parameter describes a characteristic of a population. A sample statistic describes a characteristic of the sample, just as we talked about the true mean of a population versus the sample mean, a sample drawn from that population. When we talk about a frequency distribution, it's just a way to summarize a large data set. And so we break it into intervals and just say, well, how many observations are in each interval? And we can also do a relative frequency distribution, where we have the percentages of all the outcomes that are in each interval. So that's a relative frequency distribution, and from that we can also get a cumulative frequency distribution. Now this shows the percentage of observations less than the upper bound of each interval. So it's the percentage of observations that are in that interval or any lower interval. And that's the cumulative part of it. So let's take a look at a relative frequency distribution here. Now, we've shown it in percent, but it would look exactly the same if we had the absolute numbers that were there. We could just rescale it, right? So that center one, I think there's maybe 7 observations in there, okay? And few observations in the tails. And that's starting to look like our bell-shaped curve for a normal distribution. Not exactly, but certainly the most are in that middle interval from 0 to 10%, the most outcomes. In this case, 35% of them. Well, now first focus on this left-hand side here, right here, where we've got 5% and then we've got 10%. So now when we go to a cumulative relative frequency, we start out with our 5%, and then we add some more, and that's the total. And then up here, we have the probability, the frequency, of being in all that interval to the left. That didn't show up very well on the screen, did it? Okay, so that's what we're measuring there with this height right here. And so by the time we get to the upper interval, we're up to 100%. So this is a cumulative relative frequency distribution. And what it shows you at any point, it shows you the probability of getting an observation of that size or smaller. So when we finally get to the end of the range of the variables, its highest outcomes, then 100% are to the left of that. Also, we're supposed to be able to understand a histogram, and that looks exactly like our relative frequency distribution, doesn't it? Except now we've got numbers on there instead of percentages. That's all. Same intervals as we had before. And a frequency polygon is the same thing, but here for a frequency polygon we've put a dot. If I can make a dot on here. There we go. We put dots here at the midpoints of every interval and connected them. So it's giving you the same information, just a different look, a different form.